Hello everyone. Today we're going to talk about the properties of expectation. The prerequisite for this material is calculus, discrete and continuous random variables, and the mean and the median. Or rather, the material and the mean and median. Our goals are going to be to define the expectation for functions of random variables and then to describe some important properties of the expectation operator. So remember that when we define the mean, basically what we said is, well, if you want to summarize a set of values, a very reasonable thing to do is to just average them. And when you look at what averaging means for the samples of a random variable, essentially what we're doing is we're summing up the possible values or integrating the possible values and weighting them by either the PMF or the PDF. Well, now let's think of a case where you would be interested in a function of the data, for example, the square, or some other function, and then you want to obtain a typical value. Well, a reasonable thing to do is then average just the squares or average the function that you're interested in over the data that you see. So the way we define that for random variables is basically the expected value of the function of the random variable, which is obviously a random variable as we discussed, right? Remember that if you take a deterministic function g and you apply to a random variable a, g of a is just a random variable that it has its own distribution, its own PMF, PDF, etc. So we want the expected value or the mean of this new random variable. Interestingly, we can just we can avoid, you could potentially just derive its PMF or its PDF, but that sometimes gets complicated. You can just average it directly using the PMF or PDF of the random variable a, and that's what's called the expected value. Okay, so if this sum converges, the expected value of g of a is just all the possible values of g of a weighted by the probability of a in the form of the PMF. For a continuous random variable, we do exactly the same, except that now we weight by the density, as we justified when we talked about the mean and the median. Okay, because if you remember, we cut up the real line in these small intervals, and if you consider the average as the intervals become smaller and smaller and you have many samples of the random variable, eventually what you're doing is you're computing an integral and weighting by the density. Again, the interesting part here is that you don't have to derive the PDF of g of a. You can just weight g of a directly by the PDF to compute the expected value. So let's take an example. We have a voltage, there's this voltage across a resistor that is uniform between 0 and 1, and we're interested in the power dissipated in the resistor. So if you've ever seen circuits, or if not, I'm telling you now, you want to compute the power across a resistor, it's just the square of the voltage over a constant, which is the resistance. So now in principle, we could go ahead and derive the PDF of x and then take its mean if we wanted the mean value, because we were interested in the mean value of the power. But because of what we just said, we can do something that is simpler, which is just we average the function directly by weighting by the PDF. And remember that we said that this is uniform 0, 1, so the PDF is just equal to 1. So this is, again, what we were calling before g of v, if you want, times the PDF. And we just integrate it, and we obtain the value. So the antiderivative of v squared is v cubed over 3. So this is just equal to 1 over 3, and also divided by this constant r, which is the resistance. You can do exactly the same reasoning where you have several random variables and you compute a function of those random variables. You can just take the value of the function and then just weight it by the probability of the random variables having those values at the same time. The same for random vectors. Okay, you take a look at the function of an entry of the entries of a random vector. You can just sum it over all the possible values of the entries and multiply by the probability that those entries take that value at the same time. if you're looking at continuous quantities, it's exactly the same idea. You're interested in the expected value of a function of the random variables. You just weight by the density. And I thought I had taken away all the typos, but there's a small typo here. Okay. But again, you take the values of the random variable and you weight them by the density. Same for random vectors. Take the values of the random variable, you weight them by the density. We're going to see an example in a moment. This gets very, very long because we have all of these possible combinations, right? We have either discrete random variables, continuous random variables. One variable can be continuous, one variable can be discrete. When that happens, when one is continuous and one is discrete, we do as usual, and we again average by weighting by the PMFs and PDFs, but in this case, we have to be careful. There's no joint PDF, there's no joint PMF, so we just use the marginals and condition. Okay, this is just a small detail. Okay, so let's do an example. So here we have a cafe and we want to estimate the mean cost of a latte, but we're not sure about the price of coffee and about the price of milk because they fluctuate according to different factors. So we come up with this model where the price of coffee denoted by C has a mean of 2.5 and the price of milk denoted by M has a mean of 3.5. And they're not, C and M are not necessarily independent, okay, in our model. Okay, so because a latte has 0.02 kilos of coffee, so about 20 grams, and 0.1 gallons of milk, now we want to compute the mean of the cost of the latte. So the cost of the latte is 0.02 times the price of the coffee plus 0.1 times the cost of the milk. Okay, we're assuming we don't put any sugar or anything else. So now what we could do is we could compute the PDF of this random variable of L, and we can do it in the ways that we have already learned, but that would get a bit complicated. Instead, it's much easier if we only care about the mean to just apply what we have just seen, basically put the function here and weight it by the density, the joint density, and that's very important, the joint density of these values. So now when we do that, if we expand the integral, something quite interesting happens. Because we have a sum here, we can just expand into the sums, into the sum of two integrals. And now when we take a look at this, we realize that here this constant can just come out and this other constant can just come out. And what stays inside is basically C times the joint, okay? And now what happens is that the only dependence on M here, on this part, like in this part, is in the joint PDF, but when we integrate the joint PDF over M, what we're doing is marginalizing over M. So what we're going to end up here is with C times the marginal of C, because we're marginalizing M out. Here, the opposite happens. The only dependence with C is inside the joint PDF. So when we integrate over C, what we're going to have here is just M times its marginal. Okay, so that's what we're going to get. And if you look at it, this is just the mean of C, and this is just the mean of M. This is not only for this example. When we're taking a linear combination of the random variables, what's going to happen is that we can separate it into integrals or sums. I mean, for sums is exactly the same. But anyways, of integrals that only depend on one of the random variables, then we're going to marginalize out the other, and we're going to end up with the fact that the mean of the linear combination is equal to a linear combination of the means. Okay, again, because of linearity of integrals and or of sums if these guys were discrete, and then because when you integrate over a random variable and you're only integrating the joint PDF or you're summing the joint PMF, what happens is that you marginalize that random variable out. This is a super important, by the way, then the end is basically you just have to do 0.02 times 2.5 plus 0.1 times 3.5, and that gives you 0.3 if I haven't made a mistake. Okay. So basically, the point here is that linearity of expectation, that expectation is actually linear. If you're taking the expected value of a function that you can split into a linear combination of two functions, this is going to be exactly equal to the linear combination of the expected value of those functions. And this follows immediately from linearity of sums and integrals, and this is something that we're going to use all over the place. So it's very important that you're clear about it and that you remember it, because it's a very, very useful tool. Let's see how useful it can be. If you want to derive the mean of a binomial random variable, you can remember that we described a binomial random variable as in you have n coin flips. Each coin flip has probability theta of being equal to heads. So now how many heads do you get? You can express this as a sum of n Bernoulli random variables that are equal to either 0 or 1. They're equal to 1 with probability theta, and then you just sum them up. That's going to give you the number of heads in the example. That's going to give you the value of the binomial. So you can express a binomial as the sum of n independent Bernoulli random variables with parameter theta. If you only want the mean of the binomial, then you can apply linearity of expectation. So here we have the sum of the Bernoulli random variables. By linearity of expectation, we can take the sum outside, and now the mean of each Bernoulli is just equal to the parameter theta, so that we get that the mean of a binomial random variable is just equal to n of theta. We have not even have to define the PMF of the binomial to do this. So as you can see, because of linearity of expectation, it is often very, very easy to compute the expected value of things really, really quickly. An interesting thing here is like a quick question is, have we used independence in this argument? And we have not. Okay, linearity of expectation actually holds whether you have independence or not. So here our coin flips are not necessarily independent. If they weren't independent, then it wouldn't be a binomial anymore, but the mean would still be the same. Okay, even if the coin flips are so dependent that they all yield the same value, because they're completely correlated, then even in that case, the mean would still be this. So this is what PMF of a binomial random variable with parameters n equals 20 and theta equals 0.5 looks like. The mean is at 10, as we have just derived. Another important property of the expected value is that when you have the expected value of two random variables of functions that only depend on each of two random variables, and these random variables are independent, then the following happens. When we take a look at the expectation, again, we take the function of interest and we weight it by the joint. But now, because these random variables are independent, the joint is going to factor into the product of the two marginals. So we can separate this on the one hand into an integral that only depends on A, and then on the other hand, an integral that only depends on B. And of course, this is the expected value of A, and this is the expected value of B. So if we have a product of independent random variables and we want to compute its expected value, it's going to factorize into the product of the expected values. But this only happens when you have independence, because you need the joint to factorize into the product of the marginals. Otherwise, this does not work. Okay, this also holds for discrete random variables. Now we're going to take a look at a case where this indeed does not work. So imagine, there's the owner of a restaurant, and she's trying to estimate the expected revenue. She realizes that the mean number of customers is 50. she sees that the mean amount spent per customer is $40. So then you would argue, by if this was true, okay, if this was the number of customers and this is the amount per customer, like multiplying should give you the revenue. You can either multiply before an average or average and then multiply. If the two quantities are independent, we have just proved that this is going to be exactly the same. However, in this example, the owner checks and it's not the same. Okay, and what is going on? Well, what's going on is that in that case, these two quantities are not independent. So you have to be very careful with that. And now I'm going to show you a cartoon example of how these two quantities are actually not the same if the random variables are not independent. Imagine that each night is busy or calm at the restaurant with a probability of 1/2. On busy nights, we always have 80 customers. Again, this is a cartoon example. And each of them spends $60. On calm nights, we have 20 customers and each of them spends $20. So what's the mean number of customers? It's 80 divided by 2 plus 20 divided by 2 because the probability of having a busy night or a calm night is just 1/2. So that equals 40 plus 10 is 50. And then the mean amount per customer, okay, so 50 is the mean number of customers. To compute the mean amount, same thing, 60 divided by 2 plus 10 divided by 2, that's 40. But now let's take a look at what happens if we first multiply and then take the average. Then for the busy nights, we're going to have 80 times 60 divided by 2, if we want to compute the average, plus for the calm nights, we have 20 times 20 divided by 2. Okay, and if you compute this is actually equal to 2600, it's not equal to 2000. So you have to be careful. This product will only factorize. So it's only true that the expected value of the product is equal to the product of the expected values if independence holds. So what have we learned? We have learned the definition of expectation for functions of random variables. And we have learned two very important properties of the expectation operator, which are linearity, and also that under independence, the expectation of the product is equal to the product of the expectations. Thank you very much.